So I have a question for you. When we did our standard model with all the ingredients.
Is it okay if I ask a question first?
Yes, please.
So yesterday when we wrote the Euclid Lagrangian, I mean we wrote everything, but we don't have any Lagrangian for the left neutrino. Is that because we don't have a right neutrino?
Let's write out Yukawa interaction, right? This is the question.
Yes.
Remind me your name, please.
Sarang.
Thank you. Actually, it's good that you remind me. When you ask a question, remind me of your name. I'm sorry. I don't see you guys. So it's, otherwise, I start knowing, you know, in class, you start knowing your students. It's very impersonal. There are some great advantages with this online. You know, you get the notes and everything. And you can be in the comfort of your home, but I don't get to know you. So Yukawa interaction, let's write it again. Well, first, we are talking about, let's forget the quarks, right? You're asking me about leptons. So this is what I wrote. This is the leptons. And I didn't write, of course. You're saying, well, you could have written this guy. Well, no. This is sort of a phantom particle. Notice, since mu r would by definition has charge 0 and T3 is 0, it's a singlet, therefore the hypercharge also would be 0, you agree? So it has no standard model quantum numbers. It's not part of the standard model. Because some people say, oh, you should include it. Why didn't they include it? Okay. They didn't include it because they wrote the theory of natural phenomena describing the world in which we live. You don't introduce the particles that do not exist unless your philosophy, your principle, your idea, your structure forces you to that. It would be very strange to put a particle which has no quantum number, which doesn't know anything about the standard model. So clearly, I cannot overemphasize this. That would be crazy. It will be not understanding.
Yes,
this is
I
not.
have the second question.
Sorry.
So we say.
Yes. Hello. I lost you.
Yeah, can you hear me?
Now, yes, but I lost you before.
I think it's internet connection.
Okay.
Yeah, can you hear me now?
Yes.
So we said Z boson is not a real particle.
No, wait. Z boson? Did you say
yes.
Z boson? No,
yes.
we are talking about. No, wait. I didn't answer yet. We are talking about neutrinos, right?
Yes.
Let's finish it. So this is very important. The right-handed neutrino was not included. In other words, the standard model, let's just be clear here. It's a gauge theory of real world. This is what they wanted. In other words, it's a theory of existing particles. Sometimes your principle may postulate new particles. We talk about that, but not the right-handed neutrino. This is a quantum thing. This is a 0 quantum number. So when I write the Yukawa interaction for the leptons, then I have LL bar. We didn't finish. This was very important yesterday. This is LL. And Yukawa electron, I call it phi ER. That's all I can write plus Hermitian conjugate. And we got from here, remember that M electron, tell me if you remember, is Yukawa E times the vacuum expectation value. where we worked with phi 0, which was 0v. Agree?
Yes.
At this point, we also predict no mass term for neutrino. We'll come back to this. No analog mass term for neutrino. It's a prediction to be studied. So here, let me say, stay tuned. We'll talk more about neutrino is a fundamental protagonist of the standard model. It's a window of new physics. Today, you and I know that neutrino is massive, so we'll have to think a lot about it. We'll actually have to see whether we have missed something here and so on and so forth. But that's all I want to say, okay? Maybe next week. We'll see in a few lectures. So that was question number 1. Was what about Yukawa? Question number 2.
So we said the boson is not a real particle. Is that right?
Wait. Why would you say that? I don't understand. How can I say? Why do you call it the boson? If it's not a particle, what is it? Maybe you mean something that sorry, maybe. In what sense it's not a particle? Is electron a particle to you? No, electron is a particle. Okay, what about a muon? Is muon a particle? Let me understand your question.
Yes.
Muon is a particle?
Yes.
Then so is the Z boson. There are some particles, let me say electron. Electron is a stable particle. We never seen electron decay. So we can surely say it's a particle, but muon is unstable. So you can say if it's unstable, why do you call it a particle? It lives so little. Oh, sorry, 10 to the minus 6 seconds. I still call it a particle. Why? Because gamma muon, you can compute gamma muon from here. Let's compute gamma muon. Let's do a little exercise. Let's compute a gamma muon from here. Gamma muon is what? Is inverse lifetime. So it's 10 to the 6 second to the minus 1. But 1 second is about 10 to the 10 centimeters. You agree? Agree?
Yes.
C equal 1. Thank you. So this is 10 to the 6. Second is 10 to the 10 centimeter to the minus 1. This is 10 to the 16. No. What am I saying? I'm saying nonsense. What is, this is 10 to the minus 4, because this is minus 1. Centimeter to the minus 1 is I know that GV to the minus 1 is 10 to the minus 14 centimeters. So centimeter to the minus 1, it's 10 to the minus 14 GV, which is 10 to the minus 18 in GV, 10 to the minus 15 MeV. Agree? Gamma mu. You follow me?
Yes, I am following.
Just put, thank you. I hope the others. So notice that gamma mu over M mu is 10 to the minus 15 divided by 100. It's 10 to the minus 18. It's extremely small. So muon is almost stable. This is surely a particle. Now the Z boson. It's a gauge boson like a photon. Photon is a particle, you will say. So Z boson is surely a particle, but it's unstable. So you can ask me, well, is that really a particle? Well, remember MZ is 90 GeV and gamma Z is roughly, who computed it for the homework? Nobody?
2 point.
Okay, 2, forget 2 point, you know, 2 GeV say. So notice, again, gamma Z is much smaller than MZ, almost 100 times smaller. This is great. It is still a particle. When your decay width, so if gamma is much smaller than m, we call this a particle. If gamma is of the order of m, it doesn't make sense to call it a particle, right? It's sort of a, I don't know, sometimes you call it resonance, whatever. It doesn't live long enough for you to get to know it and love it. Not only Z boson is the particle, it's probably the most fundamental particle, neutrino, and the Z boson are probably the central particles of the Standard Model. There were windows in new physics. This is the most beautiful prediction of the glacial theory, the existence of the Z boson. I'm really confused a little bit. I even told you it's mass. So how can a particle that has a mass not be a particle? It's like saying that one of us here is not a person. Well, it could be. Your question can become meaningful only if the decay width is very big. But you know, this goes with the fact that Standard Model is a perturbative theory. This is very important. Remember, this is a crucial thing that I keep insisting. Standard Model, by definition, is a perturbative theory. We are fortunate. The couplings are small. Alpha, the couplings of the Standard Models are less than 1. Therefore, we can rest assured that gamma of all the Standard Model particles will be much smaller than the mass of the Standard Model particles. That's why the Standard Model particles are particles. Is it good? Did I answer?
Yes, thank you.
Take all the doubts away from you.
Yes.
Good.
I also have a question, Professor, following the previous one.
Yes, we said that questions are fundamental, please.
What happens when, if we consider...
Remind me of your name.
I'm Eric.
Eric, hello.
Yes.
Eric.
What happens if we consider the Majorana nature of neutrino?
That's a very good question. I can't yet even speak about that. Neutrino is massless. So I'm not allowed to speak about that. Remember, we speak of what we know, but we don't know yet how to get neutrino mass. This will be a lecture, maybe on Friday, if not next week. It's a very important question. But you agree, neutrino has to be massive. For massless particle, there's no sense of speaking of Dirac, Majorana, whatever. Massless particles. So, okay, let's just write down so that we have a memory here. So I think I answered this question number 3. What about neutrino? Is neutrino Majorana? No, not here, not in Standard Model. Why? Because mu is 0. This is what we call a wild spinner. Just to see whether you know what you're asking me, what would you call a Majorana spinner? So now I ask you back.
When the charge conjugate particle is the same as the...
Very good. So Majorana particle is, let's call it nu Majorana equal to nu Majorana C, right? Charge conjugate. This is equivalent. We will find out that you can write a Majorana mass term. You had this in the homework. This is a Majorana mass term. So to be Majorana, you need to have a mass. When you are equal to your charge conjugate, that means you violate, obviously, any global symmetry. Remember, nu MC is C nu M bar transpose. So this is C gamma 0, nu M star. So that means Majorana is crazy. Majorana is a fantastic particle, wonderful, strange particle that is equal to its antiparticle. Majorana is a half-time particle, and half-time is precisely antiparticle. Cannot decide what to be. We have to talk about it. But not yet, because I have to understand how it gets a mass. So, obviously, stay tuned. This is the question that, fortunately, the standard model, this extraordinary high precision theory of all the known interaction, finally we know today is not complete. Stay tuned. Why? Because standard model, it's not a wrong theory, just like Newton cannot be wrong, but it's not complete. It's not complete. Why? Because in the standard model, m nu in the standard model is 0, but m nu in nature, which is experiment, is non-zero. How do I know that neutrino is massive? From which observation comes?
Solar.
Neutrino oscillations, you mean?
Yes.
I wouldn't know from solar neutrinos that neutrino is massive. Neutrinos come, billions of neutrinos as I speak now, as you know, billions of neutrinos are every second passing through every centimeter square of my body and your body. So it's not because of solar neutrino, because of neutrino oscillations. By the way, solar neutrinos was very hard to see. So you should not see solar. It's even harder to, to prove that it's oscillation. What does it mean that it's an oscillation? Now that you ask a question and we have to discuss it, someone may tell me, what does it mean that neutrinos oscillate?
Do they change flavor?
Yes. In other words, what happens is that, for example, nu E can go into nu mu, you agree? Or nu mu can go, I don't know, into nu tau, where by this I mean, I pretended now that there is one generation, I call it nu E, but of course, there are other generations, we'll come to, up to now I'm speaking only here, but very soon I'll have to add that. And then there is also third generation. So I can oscillate. It turns out that this first oscillation is what is called the solar oscillations. This is what happens in the sun. This is in the atmospheric. But what happens is let's see if you remember, what is the probability that, for example, nu mu, it doesn't matter which one, goes into nu E into nu mu. Now that we ask that, I'm making a little digression, which will help us. I'm reminding you of what Smirnov told you. How can we derive it? Let's derive it being lazy. Let's call this a derivation. In order that they oscillate, they must mix, you agree? There must be flavor mixing. You remember that? Otherwise, how will they? Flavor mixing needed. So the probability to oscillate must be maximal when the mixing angle is maximal. When is the mixing angle maximal? When is the mixing angle maximal?
When it starts from one flavor and changes completely to
right. When is it maximal? It's a mixing. When is that number maximal? 145 degrees, 383 degrees, 1,000,002 degrees. When is the mixing maximal?
When it's pi.
When
it's pi.
No.
Pi over 2.
Okay, pi 0. Pi is just a, you know what I mean? Look, what I mean the following. That nu e nu mu is cosine theta, sine theta, minus sine theta, cosine theta, nu1, nu2. This means the mixing. This is flavor. Look, the way I defined it. I thought you knew oscillations. You know, if I talk to Alexei, he says, oh, I do this at length. And these are what? These are flavor states. We call them flavor states. Why? Because they accompany flavor. You see, electron has a certain flavor, nu e. What are the nu1 and nu2? Which are these states?
Mass eigenstate.
Mass. Great. Thank you. These are the physical states. They cannot oscillate. You know, I cannot oscillate into Eric. That cannot happen. Eric is Eric, I am I. So nu1 can never oscillate into nu2. Nu e can oscillate into nu mu because nu e is not a particle. And when you produce in the sun, for example, something, you produce nu e because there is only electron in the sun, for example. There's no muon in the sun. So when is this maximal? When is theta maximal? Look, if I take theta equal pi, you told me, let me try one solution, theta equal pi. Cosine theta is -1. So this becomes matrix -1, 0, 0, 1. This is minimal mixing, not maximal. There is no mixing. I need maximal mixing. So this is minimal mixing.
So it should be 45 degree.
Yes. What's your name, please?
Arpon.
Arpon. Yeah, Arpon, sorry. Actually, I remember it and I forgot. Okay. This is pi over 4, obviously, because look what you got. You get 1 over square root of 2. 1 over square root of 2. -1 over square root of. This is maximal. You can't mix them more than that. This is the maximal mix. You can try, for example, if you take 90 degrees, just to understand, then you will get, just to take an example, take, for example, theta 3. So this is theta maximal. This is maximal. If I take theta 3, I don't know, I could take theta 3, for example, just to take theta 3 to be, for example, pi over 2. Then this matrix becomes 0, 1, -1, 0. Notice no mixing. It looks like mixing, but you are just redefining things. You are calling nu e nu2 and nu1. This is just redefinition. To get a mixing, you must get both diagonal and off diagonal. And it will be maximal when they are equal. Okay, so look, so the probability must be maximal when the mixing is maximal, and it must be proportional to the mixing. So obviously this must be proportional to sine 2 theta to be maximal. You agree? It must be proportional to the mixing. So when the mixing is small, it should go to 0. You see, because proportional to the mixing. When theta goes to 0, it must be maximal when it's pi over 2. And of course, it should not depend on the sign. So what you get, this is my derivation, okay? So this is lazy person derivation. They oscillate. So that will be proportional again to the sign. And the probability is a positive number, okay, to the sign of the oscillation length, obviously. So you will get sine square. Again, you get a square. This is just the logical thing because it has to be positive. It could be the absolute value, but it turns out to be square. We could understand that. What is needed for particles to oscillate? I'm not really teaching them. I'm trying to see whether you remember. In order the particles they oscillate.
There should be mass difference.
Right, they must be massive, and oscillation means that M1 must be different from M2. Very good. Because if they have the same mass, how do I distinguish them? What is happening? It's basically one and the same particles, precisely. So I need to get here delta M square. Is the energy difference. And it will go as the delta M square because the Einstein distribution, the dispersion relation has M squared. Precisely. It's proportional to the oscillation length. That's what oscillation means. How far you are from the source of oscillation. This has to be dimensionless. Listen to my logic, okay? Delta M square must be 0. This means that these are nu1, nu2 are actually different particles. So they can participate in this oscillation, very good. Also remember, M or delta M goes to 0 is equivalent that energy goes to infinity. If you have an extremely energetic particle with an infinite energy, then the mass basically can be neglected, right? P so much bigger than M. So that means it has to go as 1 over energy to some power. When E goes to infinity, in other words, so what I'm saying is, so here is my logic. Theta goes to 0, probability goes to 0. Energy goes to infinity, P goes to 0. L go to 0, P must go to 0. Delta M squared goes to 0, P must goes to 0. Theta is maximal, P is maximal. So here I am lazy person's approach, and dimensionally this is dimensionless. It turns out that there is a factor of 4 here. I couldn't derive that. Four is hardworking person. Derivation. But that's sort of a detail. Oscillation required the mass difference. We will have to talk about neutrino masses. This is how we know that neutrinos are massive from the oscillation. Notice that it's very important to have this oscillation lengths to be able to talk about oscillation. You should be able to vary. So in other words, oscillation pattern What does that mean? That I can talk of oscillation pattern? This is equivalent, can vary L. So the problem with solar neutrinos that you told me, the first thing is interesting, you said solar, is that here is the sun, and here is you and I. And this is the length, apparently. By the way, they actually oscillate. They don't oscillate outside, they oscillate inside. There is something called Msw Effect. Mikhaev, Smirnov, Wolfenstein. Started by Wolfenstein and then discussed by Mikhaev and Smirnov. And they actually, oscillation even happens inside. But you see what is, it is hard to vary L, as you can see. So neutrino oscillations, I'm making this a long story because somehow I was taken into it and I need to see how much you know. I cannot teach this. This is Alexei course. There is something which is atmospheric neutrinos. And what it is the following. This is now Earth. There are neutrinos, and here is someone sitting in a it's called a Kamioka mine in Japan. And the experiment is called Kamiokande. Actually super, it became super when they increased the volume of the detector. And so you guys are sitting there, you don't have to be Japanese to do that. This is a very big international collaboration, as you can imagine. There are neutrinos bombarding you from above. By the way, I need help. How do I get neutrinos in the atmosphere? From where? Which process?
Is it inverse beta decay?
How do I get neutrinos? Inverse beta decay. Inverse beta decay is neutrino hitting on the proton. You're telling me how I see that I got a neutrino. That is different. How did I get this neutrino? Where is neutrino coming from? Not what I'm going to do with it. How I will see it, it's my, it comes later. Where this crazy thing comes from?
In cosmic
neutrino.
rays.
Huh?
Cosmic rays.
Okay. How am I going to identify neutrinos in cosmic rays? How will you know? What energy does it have? Who is this guy? In cosmic rays, thank you, you're going to have what? You're going to have protons and stuff like that. You agree? A very interesting particle you get when you have protons in strong interaction. What?
Muons.
How do I get muons? You remember pions? You do?
Yes.
So how do I get a muon? I need a neutrino. I don't need so much a muon, really. I need a neutrino, but I can get both. Because pion, for example, can decay into what? It can decay into an electron plus nu e bar, or muon. We call it a bar because we associate the lepton number. So I call it bar. That's just a name. Or muon plus nu mu bar. So what happens when pion decays? Which of these two is more important? Which dominates?
Electron.
Why? And muon. is much bigger than M electron. So you're saying electron has much more phase space. So you are saying electron dominates. So I could neglect this. Correct? Correct? Agree? People agree? Or disagree? I need some input.
I agree.
So I'm saying right, wrong. This is completely wrong. It's very interesting. Naively, it should be right. I mean, just to appreciate how strange this is, what I'm gonna say. M electron is 0.5 MeV. M muon is 100 MeV. And M pion is around 140. So it should be very hard to decay into a muon. So how can I say that this is completely wrong? Let's take what do you know about the weak interaction, please? Tell me what you know about weak interaction. What is it that I keep stressing? What is essential? We built, this is a weak interaction process, right? What is the central thing about weak interaction? I keep insisting.
Breaks parity.
Yes. No, not just the breaks parity. Please remember that parity violation is maximal. Anybody could break parity a little bit. What does it mean? Only left couples to W. So let's take pion minus at rest. I can always take it at rest to compare the decay rate, okay? Because it's massive. So that's a rest frame. It decays at rest. Here goes electron. Here goes nu E bar. Tell me, what is the chirality of the electron? Left-handed. So where is the spin of the electron pointing?
To the left.
Sorry?
To the left.
Helicity of psi L is -0.5.
Wow.
Not to the left, but to the right. Helicity of psi right is +0.5. Please, this cannot be, this you must know in your sleep. The convention has been going on for decades. We can't have you. This will be crucial when you do computation. What about nu E bar?
It's also on the right.
Right, because it's right-handed, because it's an antiparticle, really, but at this I mean nu EC, really. Thank you. So in other words, as said, is say +1. Let's take the z-axis in this direction. But that means that JZ is +1 because LZ is 0 along the z-axis. So this is fine, this is final. But that means that JZ initial must be +1. But that means that LSZ initial must be +1 because this is 0. A pion, what is the spin of the pion?
One.
Zero.
0. spin one fundamental spin one particles that we know, are Z boson, photon, and so on. Pion is a scalar. S of pion is 0. This is a scalar particle. Actually, it's pseudo-scalar, what we call, because it couples to gamma phi, but it has spin 0. In other words, this process is, why did I say that helicity is 0? Because M electron, here I have assumed that M electron is basically 0, which is a very good approximation because M electron is much, much smaller than mass of the pion. So this is a good approximation. This is good, very good approximation. So in other words, what is happening is this. It cannot decay into the electron. Rather, it decays into a muon. This is something that lies at the heart of the weak interaction. I don't want you to know many facts, but W decay that I gave you for the homework and pion decay, I don't know whether I have to go through the pion decay. I thought you knew it. This is why we have LXA's course, so that you people get prepared for this. It puts me, it's good that I check this, and I have to think about the rest of the course a little bit in the today. In other words, what happens is gamma, in other words, gamma pion decaying into a lepton plus associated lepton, electron on the muon must be proportional to the mass of the lepton. And of course, it will be square because it's the decay rate. So in other words, gamma pion going into muon plus nu mu bar divided by gamma of the pion decaying into electron plus nu e bar will be given by m mu over m e squared. You see, I got this result for m electron 0 because then helicity is good. Of course, when the particle mass is non-zero, helicity is not a good number. I can stop the particle, and this has to vanish in the limit ma is m lepton 0. You know, this is like 10 to the 4. So you get pions in atmosphere. And pions decay only, forget the electrons, 10,000 times less into muons plus nu mu bar. So what comes out from a pion decay? This is what comes out, nu mu bar. Of course, mu will decay. Mu is also coming, and mu decays into electron plus nu e bar plus nu mu bar. So I can calculate how much. There will be some nu e bar coming from the mu decay, and even more nu mu bar. No, nu mu, sorry. But it will add to nu mu bar. I'm just interested in the muon neutrino. I don't care whether it's neutrino or anti-neutrino. I can do the experiment without caring. So I know how much nu mu. And I sit here and I look. I get some nu mu coming from here. And I can vary the distance because they can come from here. Then they can come from here. They come from the atmosphere, sorry. So they come, you know, atmosphere. This happens around 10 kilometers, 20 kilometers above us in these violent processes when the pions are created. So I get nu mu's from here. I get some nu mu's coming from here. Look, I'm changing the distance. And then they are coming from here. And then they are coming, these guys really have to travel a lot. And what Super Kamiokande observed, atmospheric neutrinos, this is the discovery of neutrino oscillation, is the oscillation pattern. This was a great result. And turns out you don't get more electrons. So what was found out? That nu mu oscillates into nu tau, not nu e, just nu tau. This is a great result. The discovery of neutrino oscillations didn't come from solars. There were indications in solar oscillations, but nobody wanted to trust them. For many, many years, Davis and Bacall. I don't know what happened here. Are you there? Do you hear me?
Yes.
Okay. Something happened with my. I don't know what happens. Do you see a black piece here?
Yes.
I don't know how to get rid of it. I know I'm blocked. So what to do now? Something strange happened. Let me try to erase it. No, it's all blocked. So the only way, it seems, in order that I progress, I guess to have to turn off. Let me just finish on this word. So you found in neutrino, in the atmospheric neutrinos, that nu mu disappears. And it depends on the length. And I think the only solution is here. I don't know whether you guys have any experience, is that I disappear for 1 minute. I turn off my iPad and turn it on. You bear with me, please? Okay, don't leave. I don't have any other option. I'm blocked. Okay, so wait for me.
Wọ́n yóò lọ sanwó sí. Wọ́n yóò lọ sanwó sí. O ìméèlì ni. Nígbà tí ẹ̀kẹ́ wá sẹ́ni bẹ̀rẹ̀ nínú lóṣù tìdó. Ifá náà. 36.
Hello, everybody. Can you hear me?
Good, I'm not starting at 11. So let's go back to broadcasting. I hope it works now. What a funny problem. It seems it's okay, right? You're there? I have you?
Yes.
Okay, so let's go back. Remember, I did my little derivation. I just sort of argued here. This is our derivation formula. Famous. Look, I said it must be proportional to mixing angle. It should be maximal. So I know this. And what they found out, actually, they can vary L. This is beautiful. So let's go back to our picture, okay? Now that I've actually, it's funny, I gave a completely different lecture for what I was planning. And please, this is just sort of a telegraphic review that where is the picture? Sorry, I should go back to the picture. I don't know why I went down. Here, I can vary lengths. You know, here, for example, L is about 10 kilometers. But when it's coming from here, L is, what is it? About 12,000 kilometers. And so on and so forth. So they managed. So what these people managed to do by varying the lengths, they found that theta, we call it theta atmospheric, the mixing angle. It's not really 45 degrees, but it's close. Just to remember it. And delta m square atmospheric. Someone remembers roughly the number? Just roughly. 1 GeV, 10 GeV squared, 10 to the 19 GeV, MeV squared. Just give me an idea of the order of magnitude. Neutrino mass. Huh?
But is it like 1 GeV?
1 GeV?
It's 10 to the minus 4 eV.
Oh, that's better. If it was 1 GeV, then neutrino mass would be GeV. Look, if this was GeV squared, which is M2 squared minus M1 squared, that would mean that M is bigger than GeV. But then neutrino would be the heaviest particle of the leptons, not the lightest. Why would we even speak about the mystery of a neutrino? Why would we look at the oscillations if the mass is so big? We would just go and measure it. You're almost right. It's extremely small number. This is the thing about neutrinos, 10 to the minus 3 eV squared. At the same time, we have direct measurements that neutrino's mass is less than 1 electron volt. Of course, the mass difference being small doesn't tell me what the mass is. This is from beta decay spectrum. People do this very nice. It's called endpoint of the spectrum. I don't know if I should remind you of that. Alexei talks about that. There is an experiment, a very interesting experiment in Germany, Katrin. So we know the neutrino mass is less than 1 electron volt, and we know the mass difference. From here, we know that one of the neutrino masses must be bigger than the square root of 10 to the minus 3. Which is some number roughly 1 over 30 electron volt. Obviously cannot be smaller. If all the masses are smaller, then the mass difference would be smaller. So this is how we know neutrino mass. There is also the solar oscillation. I don't want to talk about that, but now that I mention it, and it's a very interesting thing. The neutrinos oscillate inside the sun, Msw effect, and what we learned, this is very interesting, theta solar. Someone knows roughly? Those of you interested in neutrinos, please, you cannot be interested in neutrinos if you have no idea, roughly. I'm asking, what is delta M squared solar? Roughly. It's much smaller. It's 10 to the minus 5, maybe a little bigger. And this is about 30 degrees. And I stop here. This is a detail, and you will forget it, it seems, because Alexei told you and you don't care about the numbers. I can see, of course, if you are telling me that you are interested in more formal thing, I understand you. When I was interested in formal things, I didn't know the numbers. I don't want you to know the numbers precisely, just to have a feel, just sort of roughly, you know, just like in real life. You like to have a feel for numbers. If someone is very light, you know, if I weigh 100 kilograms, you will say, oh, you are not light. But if I weigh 60 kilograms, you will say, oh, you are light. Okay. That kind of feeling. Bottom lines, neutrinos are massive. And we have to talk about neutrinos are massive. This was a reminder, please ask me more questions. Stay tuned once again. You could profit to ask me questions now if you wish on anything that I obviously, this is not a part of my standard model teaching. This is a desire. I want to make sure that you know the basics. If there's anything about the pion decay, I mean, I was here reminding you. I try to do it coherently. I hope I have convinced you of the oscillation formula. We can derive it. We could include it in the, well, it's in every book. It's very easy to derive it, but I don't want to do it here. Okay. Look, if you don't ask me anything, I'm going to stop here and I'll go back to my standard model. I have a question for you before I take a little break so that you and I can pause about what was said. I have a question for you. I said yesterday, so now we go back to our standard model Higgs. We are studying the Higgs mechanism, right? We are fully engrossed in that. And what I took phi 0. I call it Goran is 0V. Then we had some phi 0 us, or you, I should have said, you can say, which is V0. But that was sort of, you immediately knew if I go from one to another, it's like saying here Q is T3 plus Y over 2. And here you can take Q is T3 minus Y over 2, which is reversed there. What happens if I take phi 0? Devil. Someone that wants to drive us crazy, in your opinion. How can this work? Anybody can tell me what will really happen? How can this reproduce? How can it be that this vacuum, I need to have Q electromagnetic acting on phi 0 devil equals 0. No, this is very strange. How does it work? If you don't have a clear answer, then I want us to discuss this a little bit. I'll try to help you understand this profound issue. But if you have an idea, it's your chance to say it now. What you think happens. For example, I have a question, really precise question. If this is phi 0 devil, so I have a question now. The lepton, is this the lepton field? Is it? So it seems you haven't thought about that. Okay, so answer after the break. So let's meet at 12:10. It's now 12:03. Let's take a few minutes after the break. Let's discuss this. Please think about it if you wish for these 7 minutes and try to guess. I don't even need you to be right. Just tell me, what do you think happens with the fields I introduced? You're allowed to say now, if you wish, before I get up. If you have any idea that happens, okay, it can be wild. You don't have to be sort of, okay, after the break. Let's meet in 6 minutes. Sorry?
Is QEM 0 in that case?
Is what, Q?
0, the 0 matrix?
Q. I don't understand. The Q is 0. I'm confused.
I mean, we cannot find any combination that gives us
But how can that be? But I have the right to choose vacuum like this. It cannot be like that. No, there must be a physical picture. It's not trivial. Think about that for 6 minutes. Let's meet at 12:10. It's not trivial. It's not so hard, but it's not trivial. Okay. I get up and make myself another coffee. Okay, 12:10, we are back. Any thoughts on this? Or you want me to proceed?
I thought about it. So first of all, we can always think about a rotation in the, in the SU2 dub,
SU2 rotation, very good. Like, you mean going from one vacuum to another?
Yes, in the...
Very good. In other words, sorry, yes. So we have these two. There is phi0 devil. We can always say that this is you. Presumably, this is what you mean, phi0 Goran, right?
Yes. So in
this
that...
is an S. If you find this rotation, the Q0 devil must be something like U, not Q0, sorry, Q electromagnetic. Is U, Q Goran, U dagger, something like this, right?
Yes.
Right. Something like that. Let's talk a little bit more about it. Very good. All we have to find is U. It won't be very hard to find this U. But let's do that first. I wasn't gonna do that first, but let's make for happy and let's do this. Let's do this first. So all I have. So what is U? It's some unitary transformation, right? All we are saying that U dagger U is 1. Okay. And by the way, this can be SU2 cross U1, so the determinant doesn't have to be one of U. We have a U1 symmetry at disposal. So all I need to have this. So in other words, V1, V2 is U 0V. Remember that V1 square plus V2 square, let's take them real for simplicity. We can take them complex, but let's take them real, is equal to V square. That we know. Why? Because we know that phi0 dagger, phi0, it's always V square. M0 is set of all points for all 3 0, all. Whether it's devil or Goran, whoever, everybody has to satisfy that. So in other words, U11, U12, U21, U22, 0V is V1, V2. Which means that U12 V is V1 and U22 V is V2. So U is equal to U11, which I don't know, V1 over V, U21, V2 over V. And I have the NU dagger is U11 star, U21 star, V1 over V, V2 over V. You have to check me because I wasn't gonna do this now, so I'm now doing it. I can be wrong, so please check on me. So UU dagger. What is UU dagger? U1 square plus V1 over V square. This one I'll take to 2 is U21 square. This is easier for me to see, plus V2. I can do this order over. What about the 1-2 term? It's U11, U21 star, plus V1, V2 over V square. And here is the complex conjugate U21, U11 star plus V1, V2 over V squared. This must be 0. This must be 0. This is 1. And this is 1. So I know that U11 is proportional to V2 over V. I have to think of the sign. And U21, so I have the sign freedom must be minus V1 over V. Now it works. This is one possible sign. I think I'm right. Please check me. V2 over V. This looks good. V1 over V.
Could I? I was just thinking, as long as we are considering only real fields, real V1, V2, and V, then we can think about like cosine theta and sine theta.
Right. This is precisely precisely what you said. U is real now, so it's an orthogonal matrix. You agree? And this is precisely cosine theta, sine theta, minus sine theta. I should have written immediately. I could have done it more elegantly. I wanted to be pedestrian, but you notice where cosine theta is V2 over V and sine theta is V1 over V, which has to be satisfied because cosine squared theta plus sine squared theta, it's correct. It's V2 squared plus V1 squared over V squared, but this we notice is 1. I perfectly agree with you. But you can generalize it. We can put a phase if you wish. You can, a devil can even take V1 be complex. I don't want to do it. You can do it. You understand what is going on. So it's very easy now. I don't want to do the calculation. You can find Q0. Look, we said Q electromagnetic devil. So let's just prove this. Acting on phi devil, phi 0 devil is equal. I said that this is U Q electromagnetic Goran U dagger, and this devil was U phi 0 Goran. This is 1. So this is U Q electromagnetic Goran phi 0 Goran, but this was 0. So this is U0, this is 0. This proves it. This works. It's just the famous possibility of unitary transformations of your generators. It's like going from Pauli basis to whatever basis. Okay, this is equivalent to saying, as you know, if you have TA, TB for any group, it doesn't have to be even SU2 epsilon, sorry, F, A, B, C, T, C. It's very easy to see from here that U, TA, U dagger, call this TA, what shall I call it, prime, then TA prime, TB prime, it's easy to see is I, F, A, B, C, T, C prime, because U dagger is 1. Okay, this, you know, this is the basis change. That's what Paul suggested. We did the basis change. We went from one basis to another. That's all we have to do. I'm glad that you checked on me. I was doing it, you know, when you do it, you can make a mistake. I should have done it, but I didn't want to be intelligent on purpose so that you sort of see more pedagogically what is going on. But this is sort of a mathematical trick. Let's do something a little better, okay, what I wanted to do. Let's try to understand really what went on. Let's look at my, so I started with this leptonic field. And you know, I should admit to myself, I don't really know what my fields are. Let me call it psi 1 and psi 2. because I don't know, you see, I don't want to define my charge in advance in general. And this is ER, there is only one field, so I can call this dr. And I have the Yukawa interaction, let me remind you, is LL bar, Yukawa electron, phi, ER plus Hermitian conjugate, which goes into LL bar, Yukawa E, phi 0, ER plus Hermitian conjugate in the vacuum. And what we found out, if I choose phi 0 is phi 0 Goran, then it's very easy to see that psi 1 is nu and psi 2 is electron. Why? Because I get Yukawa Y vacuum is phi 0 is in the second component, so I will get Yukawa E times V, psi 2L bar ER plus Hermitian conjugate. And this means that phi 2 is an electron. Of course, left-handed, so it's EL. Psi 2 is an electron. This implies that psi 1 is the other state, which I call neutrino. By the way, it checks because Q Goran was T3 plus Y over 2. So if Q electron is -1, Q neutrino is 0. Because 3 goes from -1/2 to 1/2. This agrees. Neutrino is the neutral guy. But you see, this is for phi 0 Goran. If I take phi 0 devil to be V1, V2, I have to redo everything. So I'm doing this not just to sort of do a trivial rotation in the group space. I want us to understand what is going on. So now, Yukawa in vacuum is psi 1L, there is Yukawa E outside, psi 1L V1 plus psi 2L V2 times ER. Agree? From here, I substitute phi 0 David. Remember that V1 square plus V2 square is V square. So what is it? This field is I know that there is one massive field, which I call the electron. So this is EL bar. In other words, I found the electron. EL is V1 psi 1L plus V2 psi 2L. By the way, let me normalize it the same way. So I should divide by V to keep the normalization. So what is nu L? Who can help me here? I need another field.
Perpendicular to this.
Yes. You see, really what is going on, and this is why we must be careful. It seems that I was doing some nonsense when I chose this vacuum. Everything fits. It's just my original guy was not what I thought it was. There is always one charge which is conserved, which is founded by using the suggestion that Paul gave. Then, of course, there will be always one electron and one neutrino, but they may be orthogonal combinations. So this is V2 psi 1L minus V1 psi 2L over V. So in other words, LL field is V1 over V EL plus V2, you see how funny it is over V nu L. I have a crazy combination, okay. V2 over V EL minus V1 over V nu L. This is what I started with. It's really a stupid way of writing. So what the devil is doing, we should have called this devil, by the way. You see, the devil should have realized But the devil is devilish, so he just wants to drive us crazy, okay? This is always, it's all consistent. Actually, we found a charge that also suggests we have a linear combination. So this, however, is not productive. It's a waste of time to do this. But at least you understand that I really now want to insist now what we have proven. We have now proven generally that we have proved that there is always a charge Q electromagnetic, which I call devil. Doesn't matter how ugly it is. It will be always some rotation on Q electromagnetic Goran, U dagger, where phi 0 devil. Now you choose any which way. You make it complex. I don't care what you do. Is U by definition phi 0, and that must be true because they live in the same space. So that Q electromagnetic devil on phi 0 devil is 0, which of course was Q electromagnetic Goran acting on phi 0 Goran. Please, there are always discussions here whether we have actually achieved something in the standard model or assumed. In other words, in standard model, electromagnetic charge is not broken. It's a consequence. It's not an assumption. It's not that I have chosen. You can tell me, no, you are cheating because you took the doublet, because you wanted one charge not to be broken. No, that is not true. Just remember, please, this is actually the result. This is not an assumption at all. Remember, when I wrote the Yukawa coupling, let's write it again, LL bar, Yukawa E phi, ER. I'm just writing leptons. You can do the, by the way, Weinberg just wrote leptons. Weinberg didn't understand the quarks, and I'll remind you why. That's what Jim did. Glesho, Ilopoulos, Mayani, some years later. He said, this must be a doublet, period. There is no choice, because this is a doublet. So this must be a doublet, must be. And we know it's hypercharged with Goran's charge, which I will never know. Now this is going to be ours forever. With these conventions, Y phi is +1. It's a doublet. It's not because I wanted to have a photon or I didn't want to have a photon. This is a consequence, okay? I must choose a doublet, okay? This is a great achievement of the standard model. In the standard model, in other words, M photon is 0, period. It's not very small, it's 0. Photon is massless. If you measure tomorrow photon mass, you must modify the standard model. That we can do. May not be easy, but we will surely be able to do that. Remember, standard model predicting neutrino mass 0, and you and I will have to modify it. And I'll have to teach you how to modify it. Was this clear?
Yes, just one comment. Instead of looking at the Yukawa term, we could have also looked at the eigenstates of Q electromagnetic in the Devil's representation.
Yes, sure.
To find out which state.
Sure. No, we didn't have to do what I did. I just wanted people to, I agree with you. We can do the same thing precisely. And by the way, that's an interesting exercise, what you're saying, and people should do it. I just wanted people to see explicitly what happens, just to understand, not just mathematically, but explicitly, that when you write, just to remember, when you write a doublet, when I write doublet, when people tell you when someone tells you, see, what was the message here? Okay, this is very important message I had. My message was the following. If I write L is equal to nu E, I already assumed the form of the charge. You cannot just write that. People can fool you. Now, this is equivalent with phi 0 is 0V. That's what I mean. If, so this was phi 0 Goran. If instead you say phi 0 us is V0, you're reversing the thing, which you can do without taking the opposite side. You can just say, okay, I will do like this. You have all the possible choices. Okay, you're doing some reversal, you're changing the charge. I will erase it because I don't want to do it. I just want to tell you that here there is an assumption. If, and then I will just write the generic one. If, however, you take phi 0 devil, which is some u phi 0 Goran, there will be also rotation, you agree. I didn't have to do it, so I could have written that LL devil is u LL Goran. I did it sort of pedestrian way, but we computed u. I could have just multiplied that u and I would have gotten psi 1, psi 2. Please check it. You will see immediately that it's one and the same thing. It's the same rotation I have taken. So there is never an inconsistency. There is no problem of taking any which way vacuum you want. But let's then agree with mine. I think that's what you meant to say, Paul. Or maybe you meant something else. I can do everything just by computing u, and everything will fit. It's a unitary rotation. All the eigenvalues are preserved. Everything is preserved under this. Right? Remember, we have Hermitian generators. In other words, if you have Hermitian matrix H and H prime is UH, U dagger, they have the same eigenvalues, of course. One of them you choose diagonal, the one, you know, any which way you want. This is what you know. This is a side remark. Okay. Is this now clear? So if I rotate on the vacuum, I'm rotating all my fields, of course, and I'm rotating the charge and so on. So when you have, for example, H on some psi is some eigenvalue psi, then of course H prime psi prime is H psi prime, and psi prime is simply U psi. This is what I have used. That's what it means going from one basis to another, just performing the unitary transformations. I have one last comment. I just have a few minutes now that we talked. We predicted MA0. Remember what we predicted yesterday? So just the masses of gauge bosons. The masses of gauge bosons, MA0. Then there was 1/2 what I called MW square, A1 square plus A2 square. Remember yesterday? W was A1 minus I, A2 over square root of 2 or plus, W plus minus. Then there was 1/2 MZ square times Z square. Boson, I'll remind you, And remember what we had here was actually 1 plus h over v squared. Does everybody remembers that? This factor came, we had v plus h, everything square, always. H goes together with v, and this you write as v squared, 1 plus h over v squared. Agree, please? Is this clear?
Yes.
Please make sure that you follow me here. I'm asking you so that you don't have to ask me. So really what I have, so this is just to remind you. So in other words, this is, so the masses. So really I'm talking about the masses and the interactions, plus interaction. Actually, I should have been more general. I have W, this is, there is a factor of 2, so this is mw squared, W plus W minus. I can put mu if you wish, plus 1/2 mz squared, z mu, times 1 plus h over v squared. I forgot to say that z was a3 cosine theta w minus b sine theta w. Up to the sign. Remember there was a sign. So I can write this a little, I can write this mw squared, w plus w minus, plus 1/2 mz squared, z squared. I'll restore the indices when I need them. I have 1 plus 2h over v plus, I don't care about this term. So the first term is mass. And this is the Higgs interaction. So in other words, the Higgs interaction Lagrangian has a factor of 2. So I will have 2mw squared, w plus w minus, plus mz squared, z squared, times h over v. But remember that mw is g over 2v. No, sorry. And this is equal to mz cosine theta w. I hope you remember from yesterday. Z is heavier, w is light. So what do I get? So v is, what is 1 over v? So from here, 1 over v is 2mw over g. Am I right? No, the other way around. Who is going to check on me? I can make a mistake. V is 1 over v is g over 2mw. So I get g mw, w plus w minus. There is mz. There is a half here. And there is g over cosine theta w mz. Z square h. As I promised, there is a half difference because w is complex. So there is actually, just to remind you, w plus w minus is 1/2 a1 squared plus a2 squared. That's why there is a half difference. It's just because w is a complex field introduced here. So what is important? The Higgs interaction please, it's very clear, is proportional to G, as you expected, the coupling of that boson. So for example, if it's If it's W, it will be GW-MW, or GZ-MZ. It's always, because remember the Z coupling, what I call GZ, was always G over cosine theta W. W is heavier, but it also has a bigger coupling. It always goes as G over cosine theta W. We found out when we wrote the interactions. We can check that tomorrow if you wish. Once again, I'll ask you to do that. The pattern goes on. You get the mass from the Higgs. Higgs interaction is always proportional to mass times the appropriate coupling. This is true for anything, any particle, okay? We have learned the lesson now what Higgs mechanism means. And this is how we can probe the Higgs mechanism. We have to talk about the Higgs. It's you know, it's the crowning achievement. That was the missing links for decades of the Standard Model. And we should try to think about its production and decays and so on. So I can stop here. I can also ask a question just to see if any of you are aware. Why was it so hard to produce the Higgs? Why did we have to wait for 60 years almost? Am I right? Yeah. Why?
I think we see that Higgs interaction is proportional to the mass of the particle.
Yes.
So
Yes.
light particles like electrons, the interaction is very weak.
So if I have an E bar machine, you are saying, for example, the coupling will be proportional to ME, right?
Yes.
And that's very small. And ME, for example, over MW, which is the scale of weak interaction, my God, is like 10 to the minus 3. No, 10 to the minus 5. Extremely small. Yes, hard to produce, of course. If there is more to it, we will learn something interesting. And what other ways you can say, what about the PP bar machine? This is E bar. What about PP bar machine or PP machine? Well, it's not the proton that matters, it's the mass of the quarks. But remember, M up, which is of order of M down, is again a few MeV. So the same problem, hard to produce. So how did we produce the Higgs? Does anybody know? How is Higgs produced? It's still hard to produce, but we manage. You don't have to answer. I'm just curious. Okay, look, stay tuned. Show up tomorrow and we'll discuss that. Think about it. What do you think we would do to produce it? You know, there are many ways we could produce it, but think about the possibilities. For example, if I want to produce it, I should produce it from the, if it's from the particle coupling, it should be a heavy particle. So I should first produce some particle that you and I know and love, which is heavy, and then produce the Higgs. This is a hint, and I stop. Give it a thought. Read about it, think about it, to discuss with each other. You know, this is a great way to anticipate your better understanding your teacher, if you care.